Alright, so welcome back to particle physics and the Standard Model. This is lecture 58, and last time we started seeing deep inelastic scattering, right. What do we mean by deep? It means the de Broglie wavelength of the scattering probe that we use is small enough that you start resolving the constituents of your proton or neutron, okay. And why inelastic? That is because when you start doing that, you actually start breaking up your nucleon, and so that means kinetic energy will not be conserved in this process, right. And we saw that the observables that are being that are used in this business are not just the scattering angle and the final state energy that you measure, but you turn them around and construct the momentum transferred squared, that is easy, but then you also construct this strange object called Bjorken X, right. And we saw that the Bjorken X can be inferred as the fraction of the proton's momentum carried by the parton. Now that does not make sense in general, it really only makes sense in the infinite momentum frame, okay. If you make measurements from this infinite momentum frame, this hypothetical frame, you will see that all the momenta are actually longitudinal, right. Even a proton at rest will look like it is moving in the longitudinal direction, in the direction of your frame, and because it is infinite momentum, you can neglect now the transverse momenta of the partons, and now it makes sense to talk about the partons carrying a fraction of the momentum of the protons, okay. So in this frame you can still construct your Bjorken X, and that is what you are actually measuring, alright. Now there is one other interpretation to this Bjorken X. It is just that if you measure xb equals 1, what does that mean? It means the parton is carrying all the momentum of the proton, right. That actually turns out to be nothing but elastic scattering, okay. You did not break anything here, right. So elastic scattering and the proton is intact, okay. But in general xb will be less than 1, and that corresponds to inelastic scattering, because now the proton is broken, okay. Why is that? That is because it means in the infinite momentum frame this might be true, but then if you come back to the lab frame, right, in the lab frame basically you have taken out the parton from the proton, okay. Okay, good. So with this in mind, we can now construct a solid approximation for how to think of cross sections of scattering of these electrons on these protons in the deep inelastic regime, okay. And that approximation, which is a very good approximation, is called the quark-parton model. Okay. I am going to write down the equation first for this and then explain what this means, okay. In the quark-parton model, the inelastic cross section, okay. Remember, cross sections can be written as differentials of whatever you want, and now we have constructed two observables xb and q squared, right. So it makes sense to write differentials with respect to those. The differential cross section I can now write as simply the elastic cross section, okay, scattering on the partons. So if you want, I can write it here also. So here it is the proton, inelastic scattering on the proton can be written as the elastic cross section scattering on the partons but with something multiplied, okay, because I am scattering on the partons, I have to write the charge of these partons, okay, in this case the quarks, right, and the key now is I am going to actually account for the presence of these partons, I just call them quarks now, okay, with certain probability distribution functions sitting out in front. Okay. So, to give some, again to give a little picture to this, this is the picture, this picture. Okay. So, the inelastic scattering is basically the sum of elastic scatterings on all of these partons, right. There are 3 quarks. So, think of the summation over just those 3 quarks, okay, for now. We will see there is more to it, but you are scattering on those constituents, and so it is an elastic scattering cross section. It has a q squared because you know you are exchanging a photon in this case, okay. But I am also multiplying with some weightage function, okay, I am giving it some weights basically for the scattering on each of these constituents has some weight or some probability. So, that is what is being accounted for by these f, okay. So, to take this again, to do this bit by bit again, this is this bit, right, that is the elastic cross section, that is e power 4 over 4 pi q power 4. This q is not the charge, right, this is the momentum transfer, okay, into some function of cos theta, especially if you have Z bosons and all that, even with photons of course. We saw that you had a 1 plus cos square theta and all, right. So, it is that is what this is, okay, like we saw for like seen for processes like this. Remember we did this E plus E minus going to mu minus mu plus and all that, right. But now we have to think of the process like this, actually it is a T channel now. You flip the diagram around, okay. So, that is why you have an e power 4, I have now q power 4 in the denominator and all that, and there are some cos theta dependencies, okay. So, that is what this part is, but the real juice of deep inelastic scattering is in that f of q, okay, because that f, right, this probability distribution function has a name, it is called the parton distribution function, also called PDFs, okay. What does this mean? I kept saying probability, what probability are we really measuring here? The thing is, this is the PDF is nothing but the probability density, okay, of finding a parton with momentum fraction, longitudinal momentum fraction of xb at a resolution scale of q, okay. Is that clear? I use a resolution scale q, right, that is the inverse de Broglie wavelength of the scattering process now, right. For that q and for that particular x, right, I want to ask what is the probability of finding that particular parton that I am seeing in the summation, okay, which I am multiplying with the charge, right. So, let me just write this is basically electric charge. Okay. So, that's that should be clear, right. That is exactly what you should be sampling. We have to see what is that probability, and then they all have to, when you do a summation, they all have to add up to 1 also, right. There has to be a sum rule for that, correct. So, now this quantity is something that you can actually measure using data in your colliders, okay. This is really the essence of hadron structure. If you get PDFs from various experiments, that literally tells you what is the structure of the hadrons. You measure this, you know what protons are made of, okay. You really know what the constituents are and how everything behaves, okay. It is not some classical picture where you have these balls floating around. No, that is not what's really going on. You really understanding the PDFs is equivalent to understanding the structure of partons, okay. Sorry, structure of protons and neutrons, okay. And that is really how you infer the presence of gluons and quarks and other things, which we are going to see now, okay. Okay. So, again I am not going to write this now, but I am going to say it in this model. The inelastic scattering on the composite proton is like the sum of elastic scattering on point like quarks, okay. That is important, point like, because we said elastic, right, of course weighted by the PDFs, okay. Now naively, right, that sum, right, this q squared f of q of x, right. Naively I would think that, how will I write this? I have a 4/9 with an fu of xb, right, xb, that is for the up quark, correct. Why 4/9? So, I have a 2/3, I square it, right, and I have a 1/9 f d for the down quark. So, naively I think this is what the sum should be, right. And how will I think? Well, how will I model the fu and fd? I will say that there is a up quark sitting in there and there are 2 of those. So, I will put a 2, and that my up quark carries 1/3 of the momentum of the proton, right, and then the down quark carries, there is only one down quark, that also carries 1/3 of the momentum of the proton, right. But of course, that is really not what is going on, okay. This is very naive, it turns out, okay, because the picture is more like this, is more like, let me draw this. If you after you measure the PDFs, this is what you see, this is xb, okay, this is 0, 0.25, 0.5, 0.75, 1, and the y axis is whatever it is, okay. There is no real units here to speak of. It goes like this, okay. So, the up quark actually, it does actually peak near 1/3, but it is not a delta function, okay, and it is not really just the up quark either actually, okay. So, okay, I am not drawing it really well, but you can imagine. Okay. What I have drawn here is actually the PDFs of the up quark minus the anti up quark. Okay. And why is there a V? The V stands for valence quarks. Okay. Why do I say valence quark? If I say valence, what else should be there? There should be some C quarks also, right? Why is that? Let us see. So, let me draw it first and then I will tell you. So, for instance, I will have some PDF like this. Okay. For the C quark, I am putting an S down here, but it's an anti quark. Okay, anti D, and then I have other PDFs for C bar S basically. Okay, and so on. Another important thing to draw would be another valence quark, and that is D V, which is nothing but D minus D bar. Okay. So, this looks roughly what you expect if you forget about the C quarks. It peaks at 1/3 and then the U valence quark distribution is twice the D valence quark distribution, except we have all these other features also, right. Any guesses for why we have these features? Why do we have these C quarks? Simply because when you have quarks flying around, what else happens? You will also you'll also emit gluons, correct? And the gluons can split into quark anti-quark pairs, correct? That is what you are probing here. Okay? Those are the ones that constitute the C quarks. We call them C quarks, but they are mostly anti-quarks, right? Okay. So, we are going to get into exactly that, okay, the presence of gluons. In the quark-parton model, where did we even write down the gluon? We just started writing down the inelastic cross section as a sum of the elastic cross sections of scattering on the quarks, right, not yet the gluons, correct. So, how does the gluon come into this picture? Okay, we are going to see that. Before we get there, I just want to say one thing. This plot is drawn at one particular resolution scale, which is at 10 GeV squared. Okay, and let me also just point out that this peaks at xb equals 1/3. Okay, both these peaks, right, as expected. So, all those nice things have happened, okay, but still something more is going on. Now, the way you can check whether there is a gluon or not is, let us call it a sanity check. Let us see if we have accounted for all the quarks, accounted for all the partons. Okay. The sanity check would be what is known as the momentum sum rule. Okay. What is the momentum sum rule? It is very simple. I know that if I weight the fraction, weight the Bjorken X with the PDFs, right, and actually compute the probability, right, and if I sum over all the quark flavors, then this should be 1. Is that clear? All the momentum fractions, right, they have to add up to 1 at the end of the day, and I am getting the average momentum fraction by weighting over its PDF, the PDF of that particular flavor, right. and they all have to add up to 1. What else can they add up to, right? They are all fractions, correct? But measurements tell us that for the valence dV, okay, the valence part of the down quark, that is like 0.111, and then UV is like 0.267, okay, and then all this C quarks, okay, let me just write C here to be really clear, that is adding up to 0.168, okay, in this sum basically, okay. What do all these add up to? They just add up to 0.546, right, easily checked, and that is clearly not equal to 1, right. So, what does that tell you? That says that clearly there is a missing parton, correct, and that is exactly the gluon. Okay. So, how do we know this? Okay. How do we know it is a gluon? It is very simple actually. See, if you use a probe that is of not such a great wavelength, okay, but enough to still resolve the proton structure, right. So, then you will see there is a U D, right. Okay. So, that is what you are going to see if you do not have a very strong probe, a very energetic probe. But suppose I increase my q squared, okay, then how should I draw this? I should draw this with a smaller wavelength, right, like this. Then that is exactly where, okay, I start seeing more gluons, okay. I am going to start seeing some more gluons. So, I have a UUD, that is for sure, but then this is exactly where I start seeing gluons. Why is that? Because if you were to have a lot of resolution, this is what you are going to see, right. Inside I have these 3 valence quarks basically, and then they are basically exchanging these gluons, right. And those gluons can split off into 2 more gluons, correct. There can be so much more splitting going on all over the place, right. This gluon can split off some more, right. This gluon can further split off, blah blah blah, right. So, you have all this seething structure, and this is exactly where I also get quark antiquark pairs all over the place, right. So, that is really the structure inside, but to really see it I have to probe the structure deeper and deeper, right. So, as I increase q square, that is when I will see there are more gluons, the PDFs of the gluons will actually increase, okay. And then if I increase it further, let me just draw one more of this. If I increase the q squared even further, then I have I still have the UUD, that has not gone away, but now I will see a lot more of the gluons, okay. Now I have to draw the wavelength really small, okay. So, this is exactly how we discovered the gluon, by increasing the resolution scale and seeing more and more of this extra missing parton, okay. So, to draw a rough diagram, plot of the PDFs, if this is xb times fg of xb, and if this is xb, then I have at high q squared, the PDF looks like this, and then as I decrease q squared at low q squared, the PDF will look more like this. Okay, and then of course as I increase q squared, I will get all sorts of intermediary values. Okay, so q square is increased in this picture. Of course, if you want, I can mark the 0 and the 1 in black on the x axis. Okay. So, this implies that because you see more and more gluons coming into the picture, and because they have to get into the momentum sum rule, you have to add that also in the momentum sum rule, right. So, that means all the PDFs, okay, evolve with the resolution scale q square. Okay, that is, I will have, you know, for all the PDF, for all the partons, I can think of a function like this. This is a pretty intricate function. Okay. Okay. So, we are coming to probably, you know, the last lesson here, which is that in deep inelastic scattering. I will just wrap up deep inelastic scattering here, which is that these F's, right, the PDFs themselves, right, they are themselves not calculable from first principles. Okay. Why is that? Because this is in the regime of non-perturbative QCD. QCD has strong, you know, it has a large coupling constant, right. So, you can't really do perturbative expansions, no Feynman diagrams and so on. Okay. So, this is not calculable. However, it turns out that this quantity, right, the evolution actually with respect to the resolution scale, that is calculable. Okay. And that evolution is given by, I am just going to give a name, I am going to ask you to go check this. It sometimes, it used to be called the Alterelli-Peresi equations, but now the modern name for it is DGLAP equations. Okay, it stands for some physicist names: Dockschitzer, Gribov, Lipitov, Alterelli-Peresi. Okay, in 2021, Peresi in fact got a Nobel Prize, not for this, but something related. Okay, so it is using this evolution that you can infer the presence and the PDFs of gluons. Okay, that is really what goes into getting the PDFs of the gluons. Okay. So, how do you get the PDFs in general? You just do some scattering experiments. You do various scattering experiments and fit the rates that you see to these PDFs. You have a lot of data across q square and you know, xb. If you have a lot of data on these events, then you can basically use the quark-parton model and some higher order corrections to it, and just see what values of the F's actually give you the correct cross sections. So, you have to infer it from data. Okay, so I will just write that here. The correct word is fit to data. You have to do a statistical fit. Okay. So, I think this is good enough for this course. So, I will just stop my discussion of deep inelastic scattering. Okay. This is literally the last lesson that we have learned in this course. So, in the next few minutes, I am just going to give a summary of what we really learnt in this course. Okay. I am going to give an executive summary so that you can understand what you really have learnt here, okay, top down perspective. So, what did we do? Remember in the very first lecture, right, so executive summary of the course. I had said in the very first lecture that particle physics is all about discovering newer and newer principles, right, not newer and newer particles, but actually new principles, and in particular but what was particularly fruitful for us was to discover new symmetry principles, right. And how what did we see in all these symmetries, right? We saw that via Noether's theorem, using Noether's theorem and conservation laws, we saw that symmetries led to stability of particle species, right. That was a very important point for why the photon is stable, electron is stable, etc., right. And then we got the concept of charge and so on, right, the usual Noether charges, okay, and Noether currents, etc., right. And then we started exploring more with discrete symmetries, right. What were these? Charge conjugation, parity, time reversal, combinations of these like CP, and the violations of all of these. And then we saw that the total combination CPT was equivalent to having basically Lorentz symmetry, Lorentz invariance, right, in a quantum field theory, correct. And then we wanted to really put all this together into a consistent framework where we put both quantum mechanics and relativity together and special relativity, and that was basically quantum field theory, correct. The fact that you have to describe the world in terms of quantum operators that are nevertheless functions of space time, right. And in quantum field theory we did not want to give up on Lorentz symmetry, so we kept that. We always started writing Lorentz invariant Lagrangians because we also take the notion of the action principle seriously. So, we construct Lagrangians and get equations of motion out of those, right. And to make contact with the standard model, we took yet another symmetry seriously, which is gauge symmetry, right, the local phase field transformations. And we saw that in the standard model it is particularly this combination of gauges that describes the field content of the standard model, correct. And along the way we saw how to construct vector fields and spinor fields and scalar fields and so on, right, in a consistent way in quantum field theory, and we put all that together, use these gauge symmetries and constructed the standard model with the correct field content. And once we did that, we actually had to break this part of the symmetry to get electromagnetism. Hypercharge and the SU2 had to be broken in order to get electromagnetism, which describes QED, right. And in that process we also got masses for the weak gauge bosons and so on. So, what was that? That is electroweak symmetry breaking via the Higgs mechanism, right. And then once we broke that symmetry, in the broken electroweak symmetry phase, broken electroweak symmetry, that is when a lot of very interesting things happened. we got for instance the CK matrix, which you get by going from the flavor basis to the mass basis in the quark sector, and you get the PM-NS matrix in the neutrino sector. And the PM-NS matrix gave rise naturally to the notion of neutrino oscillations, right, mass induced flavor change, correct. And neutrino oscillations is how we know that neutrinos do have mass, which is already a mystery because it is not accounted for in the standard model, correct. So, we constructed and deconstructed the standard model this way, okay. And once we did that, we changed gears and went into colliders, and in particular we looked at notions of the cross section, decay, obtained expressions for these, saw how people actually measure these, and then again in the electroweak sector this gave rise to the notion of the forward backward asymmetry, and all that wrapped up our discussion on electroweak, the electroweak sector. And finally in the last two lectures we saw what was inside the proton, how did people figure out what is inside the proton, experiments done in SLAC basically in the 1960s. That is deep inelastic scattering. This is how we discovered that you do have quantities that are consistent with descriptions of quarks and gluons inside the proton and the neutron, okay. And thus by experimental means also we have validated everything we learnt about the standard model of particle physics, okay. Of course the work is not done yet. We have a very good description of the world, we still do not know how to describe many, we do not know how to explain many things in the standard model like gravity, dark matter, neutrino masses, why are there 3 copies of matter, okay, what the cosmological constant problem, all these things, right, why are there more baryons than antibaryons, the matter antimatter asymmetry. So there are so many problems still remaining for which we do not really have a good answer in the standard model. So it is very much a work in progress, and I hope that you find these mysteries at a fundamental level exciting and motivates you to learn more about the natural world in terms of particle physics, high energy physics, okay. All right, thank you very much for taking this course, catch you later, thank you.